Hello and welcome to another video where we build an Intel 8088 breadboard computer. Today we're going to add a flash memory to our computer to be able to run a real program which will perform an actual computation. If you haven't watched my previous video, I advise you to do so before continuing. That is because if you had watched it, you would know that attaching memory to the 8086 is not that simple as it would be with the 6502 or the Z80. This is due to the fact that 8086 multiplexes or reuses the same pins for both the address and the data lines. The four most significant address bits, A16 to A19, are used in turns with some status signals showing additional information about the current bus transfer, so we need to latch those to hold the correct address. A0 to A7 are used together with the 8 data lines, so need latching as well. The signals A8 to A15 are not used to transfer data in the 8088, and these lines hold the address bits all the time, thus not requiring us to store them. I'm going to use the 74HCT573 8-bit latches. As we need to save 12 bits of the address altogether, we need 2 of these. But before we start connecting them, let me just disconnect this little clock and reset signal board for now, and these latches have their inputs at the bottom of the IC. It so happens that when we remove those resistors just temporarily, we could just plug this latch in and we've got our connections to the 8 least significant bits of the address already done to the one of the latches. Now let me put the other one in and connect all the required signals. Before we test the latches, let me add another breadboard, only to extend all the latched address and data lines, together with the control signals like IOM, WR and RD, out of the CPU breadboard, as it's becoming more and more cluttered. It will be simpler to add more peripherals later. We already extended the 8 least significant bits of the address lines. Now we need to extend lines A8 to A15, but we need to take them straight from the CPU, as these don't need to be latched. Now we've got all the A0 to A15 lines extended to the next breadboard. We only need to connect the 4 oldest bits of the address, which are latched in this other latch. We also need to remember to set any unused inputs of the latch to any state we like, because we won't use them, but they still need to be connected. Now I just need to return the power lines between the top and the bottom of the original breadboard, as I just removed them prior to putting those latches on. And also we need to connect the power between the breadboards themselves. The last and the most important signal, well, all are important, but without this one we wouldn't get our latches working, is the ALE, latch enable itself. So because I don't have much space here, I'm going to move this ALE LED maybe here, because the pin number 11 on these latches is the ALE. So now we just need to connect the CPU signal to the both latches pin 11. We've now extended all the address lines, all 20 of them, to the next breadboard, but we forgot about the data lines, so we need to just extend them out of the CPU to the second breadboard next to these address lines. And finally, let's extend these three control lines, IOM, WR and RD. Of course, currently those LEDs wouldn't work because I need to first bridge those together. Since I connected the bottom half of this breadboard with the top one for these three LEDs, I think I should do the same for all the data and address lines as well. Before we add the flash memory, let's check if our latches work as expected. To do so, I'll reconnect all the LEDs for the address lines and the data lines as well. Okay, the address lines and LEDs are now connected. Now to put the LEDs in the data lines, because now we need separate LEDs for the data, I'll try to do them at the bottom because I have not enough space for the LEDs at the top. It looks like finally we're done. Just don't forget about our 8 resistors, which are pretending to be our program memory with the NOP hard-coded instruction, which is, remember, 90 hex or 10010000 binary. Please trust me, I did connect those resistors, or I believe I did, correctly, because there was a little bit of mess on my breadboards. I believe that this resistor goes to high level, which is the oldest one, so it's 1. These two go to this common ground 0, 0. The next fourth is going to 1. Then this one goes to 0, and 3 least significant bits go to 0 as well. I think it's finally a good time to connect our clock and reset little breadboard just to test our latches. Okay. Let's power it up. Oh, we've got something, and I can already see that our resistors work as I intended. We have the NOP, which is 10010000 on the data lines. Now the CPU, remember, is in a random state, so we need to first reset it for at least 4 clock ticks. And now I can release the reset, and now we need to take approximately 7 clock cycles. And there you go. I think it looks promising. We've got the ALE signal active, which means this is the first of the 4 clocks during the bus transfer. And we've got our address, which, as you can see, is formed of 16 ones and 4 least significant bits. Are 0. So that's our first tick. The next tick latches all the requested address lines, and as you can see, they are still available here, while the data lines now became our NOP instruction. So the CPU doesn't drive them anymore, but we still have all the 20 bits of the address available, which is very good. So now the processor reads our NOP instruction, and the 4th cycle finishes the whole transfer. Let's go to the next one, and that's the 2nd transfer. As you can see, we've got now the following address, which is FFFF 1. So the CPU attempts to read another instruction from our data lines, which now are set to the NOP. And also you can notice that the CPU is reading because the green LED here signals the RD signal active. So that's the third tick and the last one. And we go into the third bus transfer. Now we've got a new address which is signaled by ALE active, and we've got FFFF2, which is yet another read from our flash memory. We can go through a few of those, but we can see that all the time the address lines, all 20 of them, are active, and we can use them to address our flash memory just in a second. Okay, I think it's time to add the flash memory. I'm gonna use this AT29CO10 chip just because I found it in my drawer. It is a 128 kilobyte flash, which is more than enough for our computer. This chip needs 17 address lines for accessing all 128 kilobytes. We also need to hook it up to our 8 bits of data bus and the OE signal, which allows reading from the memory. I think we're done, but the few signals, so we didn't connect yet the chip enable signal, which is pin 22 of the flash memory. I'm gonna just put it down to the ground because it's the only memory currently on the bus, so we can just make it enable all the time. Then we need to short the WR, or in this case WE, which is write enable pin 31. I'm gonna set it high because we're never gonna program it in the system. This is read-only memory for us. And finally, OE, which is output enable. We just need to connect, this is pin 24, to our RD signal of the CPU. I think it is going to be that pin in here. We're going to tidy up all the cables in the next video when we add RAM memory, so this bottom part will be kind of memory part which we will never touch later again, and we will build up our computer upwards using the signals extended on the third breadboard. I think we're almost ready to power it up. Just don't forget to remove those resistors. We won't need them anymore. We will use our flash memory here to execute a real program. And of course, as ever, I forgot to power up our third breadboard with our flash memory. And of course, we need to join the top and the bottom part together. The current schematic looks like this. Before we write and run the first program for our computer, let me tell you a little bit about the AT86 architecture. It is not supposed to be a comprehensive tutorial, just as little information as required to understand our program in assembler and the design decisions we will have to make very soon when introducing the RAM memory to our computer. All registers of the AT86 are 16-bit. It has 4 general purpose registers, AX, BX, CX and DX, which both 8-bit halves can additionally be accessed separately using half registers, AH, AL and so on for all 4 registers. All of the 4 general purpose registers can be used interchangeably, but each of them has a special usage in some instructions which is reflected in their full names. AX for accumulator, BX for base, CX for counter and DX for data. On top of those, the AT86 has 2 index registers, SI and DI, which stands for source and destination index, which are supposed to be used in operations on blocks of memory. For example, the processor has special assembler opcodes which needs no additional arguments and work using the SI and DI registers implicitly, incrementing or decrementing both of them automatically. On top of that, it has the rep prefix, which makes these instructions to be executed multiple times until the value in the CX counter register is greater than 0. The rep prefix automatically decrements the CX on each step. It is just one of those examples where one of the general purpose registers is used implicitly. There are two more registers called SP and BP, which stand for stack pointer and base pointer accordingly. The SP register points to the processor's stack, and the BP is intended to be used as an additional stack pointer in functions written in high-level languages. We will talk about calling conventions in one of the future videos. Since the stack obviously needs to be in the RAM, we must not use it in our first program. There is a register called IP, or instruction pointer, which, as the name suggests, points to the currently executed byte of the program. There is no opcode to access it directly, but it is changed as a result of instructions making jumps or calling subroutines. Another special register is the one called flags, which contains the bits of the current state of the processor and the results of the last arithmetic or logical operation used for conditional branching, as well as a few control bits. Finally, we have 4 segment registers, the CS, DS, ES and SS, which are going to solve our mystery of how the CPU is able to address 1 MB of address space using only 16-bit registers. The segment registers are used not only to form a 20-bit absolute address in memory, but also to logically split the memory into parts, each containing the code, the data and the stack. Each can be assigned to any part of the whole 1 MB space, and the segments may overlap. And yes, you may have already guessed, the CS decides where the code segment starts, the SS is for the stack, and for the data we have 2 other registers, the DS and the ES. The processor always executes machine code from where the pair of the CS and IP registers point at. Any operations on the stack, including accessing memory via the BP register, take into account the value of the SS segment register. All other operations accessing memory via either immediate address or those pointed by any of the general register's values use the DS register. The default behavior can be overridden by explicitly specifying another segment register. The special case is for these instructions operating on blocks of memory where the SI and DI are used implicitly. The DS works in pairs with the SI and the ES with the DI accordingly. Now, how is that 20-bit address value made of 16-bit registers? The value in a segment register is first multiplied by 16, or in other words, shifted left by 4 bits, and then the value of the 16-bit register or the immediate 16-bit value is added to that. It means that any of the 64 kilobyte segments can start at any 16-byte aligned address in memory. It also means that there are multiple combinations of the segment and pointer values which refer to the same absolute address. As a convention, we always write down the full address as 2 hexadecimal values separated by a colon. For example, if the DS register is set to 1234 hex and the DX to 5 hex, we would refer to this byte in memory as 1234:0005. The full absolute address would be 1234 multiplied by 16 or 10 hex, which results in 12340 hex, and then the 5 is added making the full 20-bit address of 12345. The same byte can be addressed using a pair of different values like 1230:0045 or simply 1000:2345. It could also be, for example, 03AA:E8A5, which is not that obvious at first sight. You can check it yourself as an exercise. Before I show you our first real program, let me remind you where the processor starts executing code from after the reset. The address is FFFF0, which means that it lies in the last 16 bytes of the whole 1 MB address space. This limits us to either write a program which fits in these 16 bytes or to code a jump to a different area of the memory and put our program there. I chose to write a short program, saving several clock cycles required to execute the initial jump. This will simplify things when we trace it tick by tick. So here it is. It is just 11 bytes long, but still does some calculation, which results of we will be able to see on our LEDs. Let me go through it quickly before we actually run it on our breadboard computer. First instruction, move AX1, initializes the accumulator, or AX, with the value of 1. In this program, we use the accumulator as two separate 8-bit half registers, AH and AL, as what I mentioned a few minutes ago, the AT88 allows us to do. That means that this instruction initializes the AH, the higher half of the AX, with 0 and the AL with 1. Then we add the value in the AL to the AH with the second instruction. The current state of the AH should change to 1, as this is the result of adding 1 to 0. Then we exchange or swap the values of the AH and the AL, which at this point doesn't do much because both halves contain 1. The following instruction is going to let us see the current value of the AL. Out writes the value from the AL into the I/O port specified as its first operand, in this case 0. It doesn't really matter what address we use at this moment, as there is no peripheral which would receive this value. The only purpose of this instruction is for us to see the value from the AL register on the data bus. If you remember, in the previous video, we attached an LED to the IOM pin of the CPU, which tells between accessing the memory and the I/O. The out instruction writes data to the I/O address space instead of the memory one. That means that when it executes, our LED should turn on. Finally, the last instruction is a jump back to the add instruction, closing the loop to iterate again. Can you already guess what the program does before we start it? Let's run and see. So let's use our clock and reset signal breadboard again. Power. And then the reset signal and the clock. Okay. I think we're ready now. Ooh. Something's happening, okay. Reset. At least 4 clocks, now 7 clocks. After reset, and now we have the first read attempt, I guess. ALE is active, so we have our first address on the bus, which you already know that it's FFFF0, 16 ones and 4 zeros. Now the interesting part will be the next clock cycle, because hopefully our flash memory will return the first byte of our program. Let's see. And there you go. Now, on the data bus, we have currently 1011 1000. So the first 4 form B and 8. So B8, and this is the correct byte, because the first byte of our program is B8, which is a part of our move AX1 instruction. Okay, let's move on. Now the next byte is 01, which is correct again, because that's the second byte of our move AX1 instruction. Let's go to the third one. So this is the ALE, first LAE active. And now we've got all data LEDs turned off, which means it's 0, which is the third byte, as we expected. So at this moment, CPU just read our first instruction, which is move AX1. Okay, let's go to the fourth cycle, which is now. We've got address being read of FFFF3, and it should be 0. Let's see, and it is 0. Okay, 3 and 4. Next byte, FFFF4, which is C4. There you go. That's our second byte of our second instruction, add AHAL. That's third and fourth cycle. And now we've gotten yet another byte being addressed, FFFF5. And according to my listing, it should be 86. Let's check. 86. Yeah, correct. That's the first byte of our exchange ALAH instruction. Let's go through it. And next byte, FFFF6, is E0. And that's correct again. Let's go through. And now yet another byte, FFFF7. So this is E6, which is correct again. That means that the CPU is now reading our fourth instruction, which is out 0AL. We just need to provide it with second byte of this instruction, which is 0, and in fact it's the actual address of the IO we will output our AL register. Okay, let's read it until the end of the bus transfer. At this moment, you would probably expect that in the next bus cycle, the CPU will attempt to write the AL register to the IO port, but this may not be the case. That is because it may take a few clock ticks for an instruction to actually execute and write the result out. In these situations, when the bus would be otherwise idle, the CPU fetches the next few bytes of the program and stores them in its internal queue to execute them when it's done with the current instruction. The so-called prefetch queue in AT88 is 4 byte long. I'm guessing that before our processor actually writes the value out to the IO port, it will first fetch another byte or two of its program. Okay, let's see if I'm right. And that is our next bus transfer. Currently we have address of FFFF9. So as we expected, the CPU now reads another instruction because the out instruction isn't executed yet. And the CPU prefetches the next bytes of the program. Let's go through. Let's see when something changes. Oh, there you go. That's something interesting happening now, because our IOM signal is now active. And also, as you can see, the address is set to 0, which was our IO address we used in the out instruction. So now we know that at this very moment, the processor will try to write our AL byte to the IO address of 0. Let's see in the next clock cycle what happens. And there you go. Look, that's very interesting. Now our red LED lit up, which means that the CPU is writing. So it's writing to the IO address of 0, and the byte it's writing is 1. So the AL currently contains number 1. Okay, that's perfect. Let's go. Let's move forward. And now we've got FFFFA address, which is the second part of the jump being read now. So we expect that it will be F8. Let's see, F8, yeah, perfect. And now let's finish this bus transfer. What will happen next? That's quite interesting, as you can see, because our processor didn't jump back to the add instruction, so it's not addressing FFFF3. It carries on because it didn't yet execute the jump instruction. It just prefetches next bytes. There is nothing there, probably some zeros or maybe FF. Let's see. Yeah, it's 0. Now we've got some temporary addresses on the bus which don't seem to be relevant, and the ALE is not active, so we don't treat it as the actual address until our ALE lights up, which is now, and look at this, we've got FFFF3 on the bus, which means that our processor now jumps back to the add instruction. Okay, I'll now go more quickly through the program, and we'll see what the processor will output to our I/O from the AL register. Let's see what's the next value during the second iteration of our program. Now it writes to the I/O of address 0, value of 2. So currently AL contains 2. Previously it had 1. Let's see what will be the next value of the AL when we go through the next iteration of the loop. There we go. And currently it writes number 3. 0, 0, 0, 0, 0, 0, 1, 1 is 3. Okay, so we had 1, then 2, now we have 3. Let's see what happens on the next iteration. And there you go. It's not 4, no. Currently we have 0, 0, 0, 0, 0, 1, 0, 1, which is 5. So we had 1, 2, 3, 5. I wonder what will be the next value. The next value is 0, 0, 0, 0, 0, 1, 0, 0, 0, which is 8. We had 1, 2, 3, 5, 8. Let's go one more. The next value after 8, we have 0, 0, 0, 0, 1, 1, 0, 1, which is 13. Yes, this program generates consecutive numbers of the Fibonacci sequence. Of course, it would stop working correctly after the 12th iteration, because we used only 8-bit arithmetics, and the 13th number, which is 377, would not fit in 8 bits anymore. But that wasn't the point here. It was about showing you that our AT88 processor works in the simplest and shortest way. That's it for today. I hope you enjoyed it. If so, please leave a thumbs up and subscribe if you haven't yet done so to get notified about the next video when we are going to introduce the RAM memory to our system, design our computer's memory map, and talk about all types of the interrupts in the AT86. Thank you for watching, and I hope to see you next time.